There's a star that used to sit in a galaxy right next door to our own. It burned roughly 100,000 times brighter than our sun, a genuine supergiant, the kind of object that, when it finally reaches the end of its life, is supposed to go out in one of the most violent, most brilliant events the universe is capable of producing. It didn't. Astronomers watched it fade, slowly, patiently, over the better part of a decade, dimming by a factor of more than 10,000 until, one day, it simply wasn't there anymore. No blast of light, no shockwave visible across the galaxy, no supernova bright enough to be seen from Earth with the naked eye, the way these events are supposed to announce themselves. Just a star, quietly, silently disappearing from existence, leaving almost nothing behind to mark that it had ever been there at all. This isn't science fiction. It isn't a glitch in the data. It's a real, confirmed astronomical event, one of only a small handful ever documented, and it points to something genuinely unsettling about how the universe actually works. Some of the most massive stars in existence don't die in an explosion at all. They simply collapse silently directly into a black hole, skipping the fireworks entirely and taking a piece of their surroundings down with them into the dark. By the end of this video, you'll understand exactly what a failed supernova is, how Hubble caught not one but two of them in the act, and why the number of black holes quietly hiding throughout the universe might be far larger and far harder to detect than anyone previously realized. Let's get into it. To understand why a star disappearing without exploding is so unsettling to astronomers, you first need to understand what's supposed to happen instead. Stars significantly more massive than our sun, generally anything above roughly 8 to 10 times the sun's mass, are expected to end their lives in a core collapse supernova. For most of a massive star's life, it exists in a delicate, ongoing tug of war between two opposing forces. Gravity, constantly trying to crush the star inward, under its own immense weight and the outward pressure generated by nuclear fusion happening in the star's core, constantly pushing back. As long as the star has fuel left to burn, that balance holds. Eventually, the fuel runs out. Once a massive star has fused its way through hydrogen, then helium, then progressively heavier elements all the way up to iron, it hits a wall. Iron doesn't release energy when it fuses, it consumes it, and the moment a massive star's core turns predominantly to iron, the outward pressure that had been holding gravity at bay simply vanishes. The core collapses catastrophically in a matter of seconds, crushing down into an incredibly dense object, either a neutron star or, for the most massive stars, a black hole. That sudden, violent collapse sends a shockwave rocketing back out through the star's remaining outer layers, blasting them into space in one of the most energetic explosions the universe produces. A supernova, briefly outshining an entire galaxy's worth of ordinary stars combined, visible across unimaginable cosmic distances. This is, by a wide margin, the textbook expectation for how a massive star's life is supposed to end. It's dramatic, it's violent, and it's the reason supernovae have been observed and documented by astronomers for literally thousands of years, going all the way back to ancient Chinese astronomers recording a guest star in 1054 AD, an event we now know produced the Crab Nebula. But there has always been a nagging problem sitting underneath that tidy picture, one that theoretical physicists have quietly flagged for decades. When astronomers run detailed computer simulations of exactly what happens inside a collapsing massive star's core, a meaningful fraction of the time, the simulated shockwave simply doesn't have enough energy to actually blow through the star's outer layers and escape. Instead of successfully triggering a supernova, the shockwave stalls, loses momentum, and gets swallowed back into the collapsing core. Rather than blasting outward, the star's outer material simply falls back inward too, adding its own mass to the collapse, and instead of a spectacular explosion, you get something almost eerily anticlimactic, the entire star, core and all, quietly folding in on itself and vanishing into a black hole with barely a whisper of light escaping to mark the moment it happened. For decades, this failed supernova scenario existed almost entirely on paper, a theoretical prediction buried in astrophysics simulations, discussed by researchers like Chris Kokonek at Ohio State University as far back as 2008, but never actually confirmed by a real observed event. Catching one in the act meant solving an extraordinarily difficult observational problem. How do you prove a star failed to explode when the entire premise is that nothing dramatic happens for anyone to notice? The answer, it turned out, was patience, and a lot of it. Starting in 2009, a team of astronomers at Ohio State University, led by Christopher Kokonek and Scott Adams, began a long-term monitoring project using the Large Binocular Telescope in Arizona, systematically observing 27 nearby galaxies over the course of what would eventually stretch into more than a decade, specifically hunting for massive stars that might vanish without ever producing the bright supernova that should, in theory, always accompany a star of that size reaching the end of its life. In 2009, one particular star caught their attention. located in NGC 6946, a spiral galaxy roughly 22 million light-years from Earth, nicknamed the Fireworks Galaxy for its unusually high rate of observed supernovae. A red supergiant, roughly 25 times the mass of our Sun, brightened noticeably, then began to fade. Over the following years, the team, now designating the object N6946BH1, watched it continue dimming, using both the Large Binocular Telescope and follow-up observations from the Hubble Space Telescope, until, by around 2015, the star had become completely invisible in optical light, exactly the kind of quiet disappearance the theoretical models had predicted. But nobody had ever actually confirmed. What made the case genuinely compelling, rather than simply a star that had faded behind a dust cloud or been misidentified, was what Hubble's infrared instruments found afterward. Even though the star had vanished in visible light, a faint source of infrared emission remained at the exact same location, consistent with a small amount of leftover warm debris, and, crucially, consistent with the specific signature that theoretical models predicted a failed supernova should leave behind: a black hole, newly formed, sitting exactly where a massive star used to shine, having consumed almost the entirety of its own stellar material in the process. Adams and Kochenek published their findings in 2017, describing N6946BH1 as the strongest candidate yet for a directly observed failed supernova, a massive star that had, as later coverage of the discovery put it, gone out with a whimper instead of a bang. It wasn't a universally settled case. A separate team, led by Emma Bezor, later published research in 2024 raising alternative explanations for parts of the data, suggesting some of what was observed might potentially be explained by other physical processes, rather than a confirmed failed supernova. Science working exactly the way it's supposed to, with competing groups testing and retesting an extraordinary claim before fully accepting it. But N6946BH1 remained for years the best real-world evidence anyone had that this bizarre, silent form of stellar death actually happened in nature, and not just inside a computer simulation. Then, in 2025, everything changed, because astronomers found a second one, and this time, the evidence was almost impossible to argue with. The discovery began almost by accident. A team led by astronomer Kishle Day at Columbia University wasn't originally hunting for failed supernovae at all. They were combing through archival data from NASA's NEOWISE spacecraft, an infrared all-sky survey telescope, searching more broadly for stars that varied unusually in brightness over time. Buried in that archive, they found one star in the Andromeda Galaxy, our closest large galactic neighbor, sitting just 5 million light-years away, that brightened sharply in 2014 and then began a slow, steady decline. The star, designated M31-2014-DS1, had once shone with roughly 100,000 times the brightness of our Sun, a true supergiant by any measure. Between 2016 and 2019, its visible light output collapsed dramatically. By the time Dee's team went back to check on it again in 2023, using the Hubble Space Telescope directly, there was nothing left to see. No bright star. No visible remnant. Only a faint, reddish smudge, detectable exclusively in near-infrared light, exactly the kind of leftover glow you'd expect from cooling gas and dust, and nothing more. Because Andromeda is one of the most heavily studied objects in the entire night sky, constantly photographed by professional and amateur astronomers alike, Dee's team was able to do something the earlier N6946BH1 case never could: cross-reference the star's entire decade-long disappearance against archives from a whole range of different telescopes working across infrared, optical, and ultraviolet wavelengths, building a far more complete and airtight picture of exactly what had happened. They didn't stop with Hubble either. Additional observations captured in 2024 using the James Webb Space Telescope and NASA's Chandra X-ray Observatory added even more detail, revealing a glowing, fading shroud of gas and dust expanding outward from the star's last known position at roughly 100 kilometers per second. Material the team believes was gently shed from the star's outer layers in the moments just before its core finally gave out and collapsed. Kishle Day didn't hold back when describing what the discovery meant to him personally. "This has probably been the most surprising discovery of my life," he told reporters, and later added, describing how the James Webb data lined up with the team's theoretical models. "When you look at the JWST data, it all just fits perfectly." The findings were formally published in the journal Science, and after intensive computational modeling of exactly how the star's collapse must have unfolded, Dee and his co-authors concluded that the failed supernova of M31-2014-DS1 produced a black hole of approximately 5 times the mass of our Sun, quietly obscured behind a modest ejected cloud of gas and dust carrying only about 1/10 of our Sun's total mass, a tiny fraction of the star's original bulk, with the overwhelming majority of the star's material having simply been swallowed directly into the newly formed black hole. That model didn't just explain the new Andromeda discovery. According to the research team, it also neatly resolved several previously puzzling details from the earlier, more contested N6946b H1 case, tying both events together as genuine examples of the exact same underlying physical process, happening in two completely different galaxies, separated by years of independent observation. Here's where this story stops being simply a fascinating astronomical curiosity and starts pointing towards something with real, unsettling implications for how well we actually understand the universe around us. Every method astronomers have traditionally relied on to count and catalog black holes throughout the universe depends, in one way or another, on some kind of detectable signal marking the moment of their creation or evidence of their ongoing gravitational influence on nearby matter. Supernovae are loud, bright, unmistakable events, precisely the kind of signal-automated sky surveys are specifically built to catch. Entire global networks of telescopes exist purely to scan the sky continuously, watching for exactly that kind of sudden brightening, ready to alert astronomers within hours whenever one goes off anywhere in the observable universe. A failed supernova produces none of that. It's not loud, it's not bright. It's the astronomical equivalent of someone leaving a crowded room so quietly that nobody even notices they're gone until, hours later, somebody happens to glance over and realize the chair they've been sitting in is empty. Dr. Mansi Kasliwal of Caltech, a co-author on the Andromeda study, described the broader hunt for these events in strikingly personal terms. The quest for failed supernovae has been a long and tireless one, a search that has taken more than a decade of dedicated patient monitoring to produce just a small handful of credible confirmed candidates. That scarcity isn't necessarily because failed supernovae are genuinely rare events in nature. It may simply be because they're extraordinarily difficult to catch. As Kishaledi pointed out, most sky surveys are specifically engineered to trigger alerts based on sudden, dramatic brightening, exactly the kind of signal a normal supernova produces. A star that instead quietly fades away over years without ever spiking in brightness first can slip through that detection net entirely, even sitting inside publicly available archival data for years before anyone happens to notice the absence. In fact, that's precisely what happened with M31 2014 DS1. The relevant Neowise data had been sitting in open archives the entire time, and the star's disappearance went completely unnoticed for years, simply because no bright explosion ever triggered an automatic alert. That has a genuinely disquieting implication buried inside it. If astronomers have already found two credible examples of stars quietly collapsing into black holes without ever producing a visible supernova, simply by getting lucky enough to catch the right long-term monitoring data at the right moment, how many more of these silent stellar deaths might already be sitting? Completely undetected, scattered throughout the countless galaxies we haven't been watching closely enough, or for long enough, to notice. Every current estimate of how many black holes exist throughout the universe, how quickly they form, and how common they actually are has been built, at least in part, on the assumption that supernovae reliably announce a black hole's birth. If a meaningful fraction of black holes are instead forming this quietly, without any announcement at all, then those existing estimates may be missing a substantial, currently invisible population entirely. Step back and consider what these two discoveries taken together are actually telling us. For as long as humans have studied the night sky, the death of a massive star has been synonymous with spectacle. It's the kind of event ancient civilizations recorded in their own astronomical chronicles, the kind of event modern telescope networks are specifically engineered to catch the instant it happens anywhere in the observable universe. One of the loudest, brightest, most unmistakable events physics is capable of producing. And yet, sitting quietly behind that entire tradition of spectacular stellar death, there appears to be an entirely separate category of ending altogether. No explosion, no shockwave, no blaze of light bright enough to outshine a galaxy. Just a massive, brilliant star patiently fading out of existence over the better part of a decade, until one day, when astronomers finally think to check again, there's simply nothing left where it used to be. Kishaledi, reflecting on where this research goes from here, sounded less unsettled than genuinely excited about what comes next. All I could think about was how exciting it is to be entering this era where we'll get many, many more opportunities to study this phenomenon, he said, pointing to the growing overlap of powerful instruments, Hubble, James Webb, Chandra, and long-term archival surveys like Neowise, all now capable of working together to catch these quiet disappearances that would have been completely invisible to astronomers working even a decade earlier. That combination of tools means the two confirmed cases we have right now, N6946BH1 in the Fireworks Galaxy and M31 2014 DS1 in Andromeda, are almost certainly not going to remain the only ones for long. If anything, they represent the very beginning of an entirely new category of astronomical observation. one built not around watching for the universe's loudest, brightest moments, but around learning to notice its quietest, most easily overlooked ones instead. The slow, patient, decade-long process of something enormous, brilliant, and genuinely massive simply ceasing to exist, with almost nothing left behind to prove it was ever there at all. Somewhere out there, right now, in some galaxy nobody happens to be watching closely enough, there's very likely another massive star doing exactly the same thing. Fading, dimming, quietly folding in on itself, star by star, year by year, with no explosion coming to announce the moment it finally, silently, disappears for good. If this genuinely unsettled you the way it unsettled the astronomers who found it, let me know in the comments what you find stranger. The idea that a star can vanish without a trace, or the idea that we might be missing an entire hidden population of black holes because they simply never announce themselves. And if you want to keep following the universe's quietest, strangest deaths, as more of them get discovered, subscribe, because by every indication from the researchers themselves, this is only the beginning of finding out exactly how common these silent disappearances really are.